Okay, hello everyone. We're going to take a look at our chapter 7, sheet metal processing, shearing processing in today's lecture. We don't have a class today, but you can take a look at this quick 15-20 minute video and we will talk about shearing process in details. And I will have a follow-up quiz with this video. This will also include a little bit of true and false questions, nothing very difficult. The quiz will also be based on two topics, which are your reading assignments for today, and they will be given at the end of this slides. Okay. All right. So let's start with our shearing process. Shearing. Now, in this process, sheet metal as well as plates and bars, tubes, and various other cross sections are cut into individual pieces called blanks. Okay, typically a punch and a die are used for this process. The punch and a die subjects the given sheet to shear stresses in the direction of thickness. This operation is very similar to that of a paper punch operation. The punch and a die could be of various shapes and sizes. Some of the important parameters in this case are the punch speed, the corner radius of punch and the die, the punch die clearance, the edge of the sheet, the punch die material, and lubricant use. Okay, the punch die clearance is the distance between the punch and the die when the sheet is placed in between them. Okay. This is very important parameter, a clearance, because it determines the sheared edge quality, okay, of your finished product. Now, as we can see in this figure, we have a punch here, a die, and then a sheet metal in between them, okay, and this edge A and the edge B, which is edge of your punch and your die, is clearance C. Okay, if you look closely, what we see is when the punch comes into your sheet, cracks or a crack begins. It begins at the edge where your punch hits your sheet. Similarly, another crack begins where your die meets the sheet. Once these cracks meet each other, you get completion of your shearing operation. Okay. Next, let's look at some terminologies of our the characteristic features of a punch hole and a punch slug. Okay. Now, what do we see here? We see on the hole the burnish dimension, the penetration depth, the fracture depth, the burr height, breakout dimension, the fracture angle, shear thickness. Okay, and on your slug, what do we see here? You see the burr height that corresponds to the one on the hole, okay, the ideal slug, the rough surface, at the ends. Then you see something called a smooth surface. That is called a burnish surface, okay. In the case of the hole, this area is on the upper region, okay, since it rubs against the punch. However, in case of a slug, this region is on the lower side. This is because the area has rubbed against the die wall. All right. It is important to remember that the ratio of the burnished to a rough area on the sheared surface increases with increase in sheet thickness and clearance, and decreases with decrease in sheet thickness and clearance. Okay. Next, the next thing that we see here is the effect of clearance. All right. You can see here clearance C is very close, very small. Okay. In 2 or 7.6 A2, it has slightly increased, and in third one, it has increased drastically. Now, you increase the clearance for thicker material, but what do we see? That the sheet tends to be pulled into the die rather than being sheared when the clearance is increased. Okay. Another thing this figure shows is the hardness. What is happening here is plastic deformation of your given material, right? You can see hardness increasing. This is wicker hardness or micro hardness contours for 6.4 millimeter thickness 1020 hot rolled steel, okay, in the sheared region. What do you see? Thick hardness here is at the sheared edges are much higher than that in the rest of the material, okay. Thus your material gets cold worked, okay, during shearing process. Another important thing to remember is the distance the punch travels depends upon the maximum shear strain of the material prior to the fracture and separation. Therefore, brittle and cold work parts require little travel to complete shearing. Next, we look at the punch force. Okay. Now, if you look closely, the force is a product of shear strength of the material and cross-section area being sheared, right? The friction between the punch and the sheet increases this force significantly. Now, the shear zone is subjected to combination of deformation, plastic deformation, friction, and development of cracks. The punch force versus the stroke curve has various different shapes depending on the deformation, friction, the crack, development, and other factors. Okay, the figure shown here in 7.7 is a typical punch force versus penetration curve. Okay, the area under this curve is the work done in shearing. Now, this force, maximum force, can be given by an empirical formula, which is given on your right-hand side on the slide. F max is equal to 0.7 SUT TL. Okay, SUT is your ultimate tensile strength of the sheet metal. T is the thickness, and L is the total cutting length or perimeter of the shape. For example, for a circular hole, it would be pi d, where d is the diameter of the hole. Okay, next. Another important thing is the force. There is always a force required to strip the sheet from the punch on its way back. Okay, we will take a look at it later in some problems. Now, shearing operation. We're going to take a quick look at different shearing operations. Here, the first one is die cutting. As seen in figure 7.1, 7.8, the basic die cutting produces either punching or blanking. In punching, we discard the inside part or the hole, okay? Whereas in blanking, we keep the inside part and discard the outer sheet metal. Next, there are some other examples of die cutting. These are perforating, slitting, notching, lancing, parting. Okay, so perforating is punching a number of holes, for example. Notching is removing a piece of various shapes from the edges of the sheet. Lancing is leaving a tab without removing any material. Next is fine blanking. Okay, smooth and square edges are produced by this method. Figure 7.9 shows basic die design for fine blanking. Here you can see that the upper pressure pad and lower pressure cushion are added above the sheet and below the sheet respectively. Clearance is as small as 1%. The thickness of sheet used in this varies from 0.5 to 13 millimeters. Tolerance of plus minus 0.05 mm is usually allowed. Next is slitting. Now, in this, shearing is carried out with help of pair of circular blades as shown in figure 7.10. Okay, blades follow straight or circular or even a curved path. This is used commonly to cut wide sheets. Okay, there are two basic types to this process. A powered or where the blade is powered, and then the pull through where strip is pulled through the blades. Okay, the blades in this case are idling. There are two other processes that are described in your textbook, the sheet rules and nibbling, which you can take a look at on your own. Now, the quality of the shear produced influences the formability of the shear product, okay? For thicker sheet, the clearance is kept higher. Controlling the clearance is important for obtaining good finish. Any extra material on the final product can be trimmed off the edge by a process called as shaving, okay? You can combine the shearing and shaving in one punch stroke, thus obtaining a better finish. Now let's take a look at shearing dies, okay? The first one is punch and die shapes, how they influence our final product, okay? Remember, if the surface of the punch and tip and the die are flat, the punch force builds up rapidly during shearing, and since the entire thickness is sheared at the same time, okay? The area sheared can be controlled by beveling the punch and the die surface as shown in figure 7.12. Beveled shape is suitable for shearing thick sheets because it reduces the maximum shearing force. Next are compound dies. Several operations are performed with one compound die. They have higher productivity. However, you can only obtain relatively simple shearing with this process. Okay, these dies are slow and expensive than individual dies. Progressive dies. These parts require multiple operations such as punching, bending, blanking, and are made of high production rates using progressive dies. Okay, so remember our figure 7.13, we can see a progressive die. So first part of this shows you a washer being made. So in first step you get a hole, and then you get a blanking operation and you finish washer. Okay. The other part, B, is a forming of the top piece of a common aerosol spray in a progressive die. Okay, note that the part is attached to the strip until the last operation is completed. Next are transfer dies. In this, the sheet undergoes different operations at different stations, which are arranged in straight line. Finally, let's understand the tool and die material. Tool steel is very commonly used as a tool and die material. However, for high production rates, carbides are used. And most importantly, lubrication is used to reduce the tool and die wear and for improving the edge quality. Okay. Next, reading assignment. So in this part of the chapter, the miscellaneous methods of cutting sheet metal like bandsaw, oxygen gas cutting, friction sawing, water jet cutting, abrasive water jet cutting, laser beam cutting are some of the important processes that are quickly described in your textbook. So take a look at that, and as well as read about the Tailor welded blanks. That is end of our class for today. Once you're done with this video, make sure you read your reading assignment and take the quick quiz that follows this this particular video. Okay. Good luck. See you on Wednesday. Bye bye.